The Dirichlet series, like Taylor and Fourier series, is a popular form of series expansion. It is defined as the sum of f of n divided by n to the power s from 1 to infinity. Mathematically, it is fundamental to number theory and proofs such as that of the prime number theorem. Like other popular infinite expansions, it is possible to define some common properties. Firstly, the convolution theorem, which states that if H is the Dirichlet convolution of f and g, and H of s is the associated Dirichlet series, then if f of s and g of s converge absolutely at some point s, then so does H of s, and we have H of s is equal to f of s into g of s. Concerning the convergence of the Dirichlet series, there are two important values for the real part of S. The first is the abscissa of absolute convergence, where if sigma is greater than sigma a, the series is absolutely convergent. Then there is the abscissa of convergence, where if sigma is greater than sigma c, then it is in the half-plane of convergence. The uniqueness theorem for the Dirichlet series can be proved by contradiction. It states that for two Dirichlet series, f of s and g of s, where both are absolutely convergent, for sigma is greater than sigma a, if they're equivalent for each s in an infinite sequence that has a sufficiently large sigma, then f of n equals g of n for all n. But how does the Dirichlet series allow us to take an infinite series and obtain a finite limit, one of its most used properties in physics? This is through the Riemann Zeta Function, a form of the Dirichlet series where f of n is equal to 1 and sigma is greater than 1. The Riemann Zeta Function can also be manipulated into an integral representation. From the Dirichlet representation, it is already clear that the Zeta function is single-valued and everywhere except at s is equal to 1, where the p-series test shows that it is divergent. This gives us the motivation to split the integral in the second representation into two, from 0 to 1 and 1 to infinity. Evaluating the integral from 0 to 1 can be done by replacing t divided by e to the power t minus 1. Then solving in s is equal to minus m plus epsilon, we get the following expansion. As the integral from 1 to infinity is finite, it vanishes as epsilon approaches 0. This leaves the following finite limit for the s is equal to non-positive integers, one of the many possible analytical continuations for the Riemann Zeta function under different limits. Coming back to the finite limits of an infinite series, the Riemann Zeta function is essential, such as in Euler's argument for the sum of all natural numbers, where he assumed that s is equal to minus 1. The Riemann Zeta function is most useful for these finite limit calculations through a method known as zeta regularization, which is extensively employed in physics while dealing with the divergent series. So let's take a breath and explore its use in the shape of Casimir effect.
To go nothing neutral place as it's in vacuum they are light and parallel. The Casimir effect can be observed through this place, so let's find out what it is. The effect explains the force of attraction between places, something like Vander's force. How virtual photons vacuum fluctuation causes very smaller between the plates. Quantization of U with boundary condition. We can find the 0-point energy now. What to do infinity? Divergent series can be summed, so now regularization. We need the use of Riemann Zeta function. Come on now, follow my lead. Come on now, follow my lead. We can get a finite answer if Riemann Zeta function is used. If the 0-point energy found, quantized field tells us the force. Casimir force for Casimir effect. And finally we are complete. Every day discovering something brand new. That is all for Casimir effect.
Not limited to the Casimir effect, the zeta function regularization is essential in many fields of physics, such as the non-zero temperature string theory, finite temperature quantum field theory, covariant effective action in 2D gravity, etc. But while the zeta function appears to be so popular in physics, what about the general Dirichlet series? It is, in fact, closely linked to quantum mechanics through both the time evolution operators and joint measurements. The Dirichlet series can also be shown to correspond to the probability amplitudes of certain types of oscillators, with the sums of the series corresponding to the interference probability amplitudes. We thank you very much for watching this video, and we really hope you enjoyed it.